Hello, fellow students. Today we are going to continue studying the equivalence and order relations in graphs. Right, so I'm going to share my screen. And we are going to continue working on the problem, yesterday's problem, right? So yesterday we have this directed graph defined here by this set of vertices, the set of edges, and the application, right? And we were working with the accessibility matrix of order 1. So now we have a second question, and the second question is, calculate, if it exists, the smaller graph that contains the initial one representing an order relation, and justify otherwise, right? And the same for an equivalence relation. So let's start by the order relation. Okay, so the first step is set the diagonal to all ones to have a reflexive relation, right? So we take the accessibility matrix. Okay, let me copy this. Okay, let me pick the color black. And we are going to change the elements on the diagonal, right? So we come here and we need to change these zeros by ones. Okay, so I will mark in green the elements that I changed for to have the reflexive relation, right, in this graph. Now, for the order relation, we need to meet the reflexive, the anti-symmetric, and the transitive relation. So the next step, we already have the antisymmetric relation. So we need to work on the transitive one, right? Let's write it here. We already have the anti-symmetric relation. To have the transitive one, we need to calculate the transitive close. The transitive closure, right? So how do we do this? Well, the transitive closure is defined as the first matrix added to the matrix of second order added to the matrix of third order, and like this, right, until we meet the matrix of fifth order. In this case, you need to realize that this transitive closure is different to the general accessibility matrix, right? Because when we were calculating the accessibility matrix, we were adding also the identity matrix, and if we had 5 vertices, we only needed to add until the accessibility matrix of order 4, right? So as you see, this formula is different, right? These are two different matrices. Well, we already did this before in a previous exercise, right? And the way to calculate the second order matrix is multiplying the first order matrix by itself, right? By the first order matrix. And remember that this is logical operation, right? So I won't explain this multiplication in detail because we already did it, but is the logical multiplication of this matrix by itself, right? So we can already write the result. We multiply the first row by the first column for the first position, right? The first row by the first column, and we have ones in a coincident position here, right? So the position 1, 1 will be 1. For the position 1, 2, we multiply the first row by the second column. Right, and in this case, we have a coincident 1 on the last position, right? So the position 1, 2 is also a 1. For the third position, we multiply the first row by the third column. So you can see we don't have any coincidental 1 here. So we put a 0 on this position of the matrix. Right, we continue like this, calculating values for all the positions within the matrix. Now, if we want to calculate M3, we only have to multiply M1 by M2. Right, and we proceed like this until we have all the matrices and we calculate the transitive closure. And in this case, the transitive closure is if you make all the calculations we get this final result. So this is a transitive closure, okay? So we can conclude that this relation is reflexive and transitive, right? Because we have added ones on the diagonal, and we have calculated the transitive closure, right? But it's not antisymmetric. Right? We have lost this relation. So it does not exist the order relation order relation containing the original graph. It does not exist, let's say, the graph containing the initial one representing an order relation. It's not possible to calculate it, right? Now for the equivalence relation, we are going to start a new page. We are going to add a new page. We're going to copy the matrix here. The accessibility matrix of order 1. And we are going to copy the text of the problem. Okay, so the first step, right, is similar to the previous one. We need to add ones for the relation to be reflexive and symmetric. right? So we take the matrix and we add ones in the diagonal. And then we need to make it also symmetric, right? So we need to check all the positions where we have ones. So for instance, in the position 1, 5, we have a 1. So we need to have another 1 in the position 5, 1. In the position 2, 1, here, we have a 1, so we need to put another 1 in the position 1, 2. In the position 4, 1, we have a 1 here. Sorry, it's the position 4, 2. We need to put a 1 in the position 2, 4 here. We need to put a 1 here. Then we have the position 4, 4. Okay, this is on the diagonal, so it doesn't matter. Then we have 5, 2. We need to put a 1 in 2, 5. So we come to 2, 5. We put a 1 here. And finally, we have 5, 4. 5, 4. So we need to put a 1 in 4, 5. 4, 5. Okay, so okay, this was the original, right? This was the original, and now we have M prime. Let's call it M prime, which is already reflexive and symmetric. So now we need to calculate. We calculate the transitive closure, which is the same formula as before, right? So first we calculate the second order matrix, which I already did, right? You need to multiply this matrix by itself, right? And we get 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, and 1, 1, 0, 1, 1. So in this case, this matrix is also equals to the matrix of third order, to the matrix of fourth order, to the matrix of fifth order, and to the transitive closure. Right, but this is only for this exercise. Right, so let me write it here. For this exercise, if we calculate 5 matrices, we realize that we obtain the same result. For other exercises, it could not be the case. Right, you could need to calculate all the matrices because you are getting different results. Okay, so this is the final answer, right? We have transitive closure, which is equivalent to this matrix. And this is the final solution. This is the smaller graph that contains the original one, representing an equivalence relation. Right, we made it reflexive, symmetric, and transitive. Right, so this is the smaller one that contains the original one, representing the equivalence relation. For the previous question, it was not possible to calculate the one containing the original representing an order relation. But for the equivalence relation, as you see, it's possible. We just need to make it reflexive, symmetric, and transitive. Okay, so that was all for today. Thank you very much for joining me on this exercise. We will continue the next day. I want to tell you that if you have any question, if you see any mistake, please don't hesitate to write in the comments, right? And thank you very much for joining me today. I will see you in the next videos. Bye-bye.